Okay, so let's start the lesson for today. Do you see my screen? So for today, we'll discuss the topic on object detection. The outline for today would consist of four parts. The first is to discuss on the overview of computer vision and application. And then in the second part, we will discuss the introduction to object detection, and then some discussion on common regional proposal network such as RCNN, FastR, RCNN, and faster RCNN. And then we discuss the type of non-regional proposal networks such as SSD and YOLO. Okay, so let's start with the overview of computer vision and application. So first, what is computer vision? So there are two common definitions of computer vision. In the first definition, they said that computer vision is a scientific field that extracts information out of digital image. Okay, so in the first definition, we refer computer vision to the extraction of information out of digital image. So the input would be the digital image, and we want to extract to understand the information from that input image, right? And in the other definition, it is said that the computer vision is building algorithm, right? Okay, so the algorithm that can understand the content of image and use it for other application, right? So the two definition, I mean, they discuss different aspects of computer vision, but they are all agree about the fact that we want to understand, extract the information out of the image, right? In the nature, right? We as human, we have the eye that can capture the image from the environment, right? And also we can can able to capture the video from the environment, right? And the eye acts as the sensing device in our human body, and then that's image or video signal will be sent to the brain, and the brain work as the interpreting device. Then from that we can understand the image, understand the video, and then we can use that information for all the decision, right? And in terms of computer vision, the sensing device is a camera, right? And the camera captures the information of the environment in terms of image or video. And then that image and video will be sent to the computer, and the computer now work as our brain that interpret the image on video, and then it gives the output to extract the information about the image, or to help us understand the image, right? For example, here we have the corresponding output for the input, saying the image is about the garden, the spring, the breeze, the water, the tree, the flower, and the color is blue. Sorry. Okay, so computer vision is have a lot of relationship to other domain, other field, such as control, robotic, signal processing, physics, neurobiology, mathematics, machine learning, and artificial intelligence, right? So here we are seeing a very close term such as computer vision, machine vision, and image processing. They are very close to each other, right? So image processing is a process of transforming the input image to other image, right? So the transformation could be to improve the quality of the image or to, I mean, to improve the quality or to sharpen the image, for example, right? And the computer vision here is it can use image processing in order to do the image understanding, right? So the output of the computer vision is actual some extract information, right? Some information gain from the input image, right? The output of the image processing is another image, right? But the output of the computer vision is information, right? Had to understand the input, right? The machine vision is also a very similar term to computer vision, and in fact, that machine vision refer to the how to say the I mean, it's very close to computer vision. The difference is scope. So in machine vision, it's the processing is maybe some kind of basic task by the device to understand the image, right? But computer vision it could be other broader scope that understand the image at the deeper level, right? So the relationship between computer vision and neurobiology is that the computer vision somehow emulate the way the bio the way that bio body capture and process the image of the environment, right? And it related to the physics because in physics we have the study on the optic, right, and the way the light source reflects, and that is something related to computer vision. And computer vision use machine learning and mathematical model to process the image, right? And also it is part of artificial intelligence, right? Okay, so talking about the human eye, we have very sensitive. For example, you can have a look in the GIF in the slide and tell me if you can see anything abnormal in the image. Do you see anything abnormal in the image? What do you see in the image? You see tree, of course, right? And what's else? Can you see a person in the image? I hope yes, right? So, according to the research, it is proof that the human can process each frame, each image in only 100 milliseconds, right? For example, this picture, we never seen the picture before, but we know that in the picture there's a person inside, and we can do this effortlessly, right? So that is to say that our human eye are very sensitive, right? And however, the speed of recognizing something in the photo have some drawback. For example, in this photo, can you recognize who is this? Is it the same person or is it a different person? Yes, so the correct answer is this is they are not the same person. It is Bill Clinton and his assistant, right? They look the same, but they are not the same, right? Another example to say to show you um, the drawback of our human eye. For example, do you think that the color in the block A and the color in the block B, are they the same or are they different? From our observation, we can say yes, okay, they are different. I mean, the color in the block A is a bit darker than the color in the block B, right? But in reality, if we try to cover the surround in the of the block A and B, and we can see, oh, now you see the color of the block A and B, they are the same, right? They are different because our eye was fooled by the environment, right? We have surrounding the block A and B. Right? Okay, so the objective of computer vision is to bridge between the numerical representation between the numerically represented pixel with semantic. So the input of the computer vision is digital image. It is like a multidimensional array of numeric number, right? And and then from that input, right, the computer vision has to infer to the information from that image. So this is some kind of very difficult task for the computer at first, right? Because I mean, what the computer see in the input is that a matrix of number, right? And what we want to see is a semantic information out of that numeric metric, right? We want to understand that in that image there are train, for example, right? Okay, so the application of computer vision is vast, is very vast, and they are very, I mean, they are everywhere. First, the photo and video we have nowadays are huge, and everybody can capture the photo and video and share to the other, right? So the input in the computer vision is enormous, right? We have a different image platform for you to store the image on the internet and for free, right? Here we have what? We have the photo, we have personal photo, we have the a movie, video, we have the movie, we have sports image, we have the image and video from the CCTV, we have image and photo from satellite and from the from the medical device, right? Okay. So here's the demonstration of computer vision in some scenario. For example, people, I mean, deploy the robot on Mars, and of course, I mean, for the robot, it have to be equipped with the camera and computer vision capability in order to capture the environment and the computer vision in process and provide the robot about the information about the environment, and then the information can help the robot to navigate on the terrain, right? And here's another example. of using computer vision to reconstruct the 3D shape of a building from 2D image. Here is the image, different image in of the cathedral, and then the idea is to construct the 3D representation of that cathedral, right? Yes, is also another example of having computer vision to process 2D image and then understand the 3D space, right? Okay, so another example is to have machine vision to extract the semantic information of the image. For example, here is the object detection, object recognition. In a single photo, we can see a lot of objects, right? And by detecting the object in the image, we can understand the semantic information in that image. Okay, another example of using computer vision for 3D modeling. Nowadays, you can go to Google Street View, and you can see some monument, some famous monument in 3D representation. Okay, so it is a application of computer vision in the camera itself. We have we can the common application of computer vision in the camera is to detect face, and then from that detection, the camera can adjust the focus to make the face clear. To make the, and also, for example, to capture the smile, right? And yes, although another example of using the computer vision application to in the Apple iPhoto, right? Okay, another example, for example, here is a specific application of computer vision to analyze the iris pattern in the eye, and from that, people was able to identify an Afghan girl when she was young and when she become older in the right photo, right? Okay, so another example of computer vision in biometric, you have fingerprint scanner, and actually the behind the scene we have the computer vision algorithm that analyze the fingerprint and then can distinguish the fingerprint of different people, right? And so also here is a iPhone X-ray implemented in the iPhone device that can more modeling the 3D space of the face, and then use that information to decide if the face in the front of the camera is of the owner or of somebody else. Another example is the character recognition, OCR. This is an example implemented in the neural net to classify the writing number, right? And this is a more common, popular application of computer vision in recognize the plate of the behind. and it is nowadays also very I mean popular in our country, right? Okay, so computer vision also have to uh, to to power human computer interaction uh, in game. This is Kinect, right? So if you have chance to use the Kinect in the Xbox, you can see that you can actually navigate in the game, playing the game with your hand, and the camera of the Kinect can understand um, the the action, and then uh, use that finding to navigate the character in the game. Okay, okay, and here the application of computer vision in augmented reality. So you can, for example, merge the reality with augmented reality. Okay, this is a Pokemon game, very famous a few years ago, right? And here's also an example of augmented reality of the from the design from the design paper um, of an apartment. You can actually contract the 3D representation um, of that apartment, and then you can um, I mean you can navigate and you can view that in apartment in different angles, right? Okay, this is an example of computer vision in virtual reality, the inverse case of augmented reality. So in this case, you can, for example, uh, uh, have the feeling that you are really inside the game, right? Not playing with the monitor, but you are inside that game environment, right? And the application of virtual reality is very huge. Uh, if you if you if you read the news recently, you can see that our social network company Facebook, they want to shift the focus of the company, and they change the name to be Meta, and they want to focus on building the metaverse where everybody can have a parallel life to interact with each other, right? So I think that the future for us will be really excited because everything will be, I mean, totally different in the next few years. Okay, another example of computer vision in robotic and space exploration. Yes, it is the reconstruct panorama uh, from the different capture of the map rover robot, and from that they can construct the high quality panorama so that the scientists in Earth can understand and see well the surface in Mars, right? Okay, so that's all about the introduction to computer vision. Do you have any question? Do you have any question or discussion about the application of computer vision? Do you, I mean, are you excited about the future when we have computer vision that power the metaverse? Any discussion for you guys? I think it could be really interesting to discuss with the people about, I mean, our future. Facebook Metaverse. Do you mean Metaverse or Metaverse? Metaverse, right? I think it's possible, but yes, okay. So Phạm Văn Cường saying that it could be dangerous. Of course, I agree with you. It could be dangerous. Did you see the movie? What is the movie? Station One or what? Ready Player One. That you see that movie? Ready Player One. In that
Yes,
movie,
I have seen it.
well, what is your feeling?
I think it's unreal.
Yes, oh,
It is.
for the moment. But do you think that future is scary or is interesting? Can you have more uh, elaborate discussion on the feeling? I think you can turn on the mic and discuss a little bit about this topic. I think it's a little scary if the future turn out to be in that player one, Ready Player One movie, because you see a very big difference between the reality and, I mean, the thing inside the game, right? Inside the game, we see a wonderful world where everybody can do everything they want. But in reality, you see the world was like a mess, right? And people like forget everything in the real world and to be, I mean, 100% inside the game. So the world in reality was a mess. It's like a, a ruined city, right? Any discussion, Cường, Nguyễn Hà, Phùng Hà Nguyễn, Hoàng Anh. Okay, so I think that we can have break in 5 minutes and then we can continue. Phạm Văn Cường saying, falling for a girl in metaverse, and she turned out to be an old man. I think it doesn't matter because if you are really into the metaverse, maybe you want to really make the distinguish the differences between the reality and the metaverse, and we maybe you don't want to see the, I mean the the human behind the character. The a limited version of metaverse in VR chat that happen quite often here. Okay, so 5 minute break and then we can continue. If we want to discuss about metaverse and things like that, we can discuss if you want. Okay, so let's continue the lesson. Now we discuss the object detection, right? Okay, so let's start with different computer vision problem. In computer vision, we typically have the following four problem. The first one is semantic segmentation. So in semantic segmentation, the input is an image, for example, and we want to classify the pixel in the image to be in different object classes. For example, here we want to classify each pixel into one of four catalog, such as grass, cat, tree, and sky. So, okay, so in the semantic segmentation, the output is not is just pixel and the classification of the pixel, right? In a single object, in a single object classification plus localization, we want to detect the classify the image. I mean, classify the image into different classes and also localize the part of the image that makes that classification. For example, here we have just one object in the image and we want to classify the object and localize the object in the image, right? In object detection problem, I mean, it's a bit similar to the classification and localization, but the output could be multiple objects with the corresponding localization. For example, here we have two dogs and one cat in the image, and we want to actually detect, I mean, all of the two dog and cat with the boundary region, right? And in instance segmentation, we want to detect the object inside the image with the correct boundary. So in the object detection, the boundary is that a rectangle, but in the instance segmentation, the boundary is the correct shape of the object. And also we want to classify that object into different classes, such as dog, and cat. And also the boundary could be, I mean, separated for different object. I mean, here you see two dogs, but the boundary of the two dogs could be separated, right? Not in the case of semantic segmentation. So in this case, we can just say the classification of different of the pixel into different classes, and not about the I mean the separated boundary of different objects in the class. Okay, so the focus of the part we are discussing now is object detection, and here's the some example of object detection application. Here's the example in the smart traffic. You have the camera that I mean monitor the twist, the road, and then from that image and video input, you can actually recognize the car, the bike, and also, for example, to calculate the speed of that vehicle, right? Okay. Another example of object detection is to again detect a human on the twist, right? And here you see you can have the object detection algorithm running with a small device Raspberry Pi, and then it can, I mean, correct detect the human in real time. And here to detect the face. And you see, this is a image of 1,000 people in the festival, for example. And you see now that you can have the algorithm that can correctly detect most of the face in the image. This is another application of object detection to recognize the text in the capture of the view, for example, right? And then from that recognition of the text region, you can extract that in that region and push to the OCR module, and then recognize the character. Right? Okay, so if you have time, you can click on the slide and see the video that demonstrates the robot can do automatically picking up strawberry. Right? Okay. Okay, so now talking about the behind algorithm of object detection The first thing we want to discuss is to analyze the regional proposal network, and the kind of network is considered as a two-state object detector. So okay, so let's discuss about regional proposal network. So the basic idea of doing the object detection in the image is to use a sliding window approach. So for example, you have the input and you can have a small configure window, right? And what you do is you will slide the window over different places in the image, from left to right and from top to bottom, and then you can try to classify if that window belong to an object or not, right? Okay, so sliding algorithm is window approach is like this. You scan the window from left to right, top to bottom, and at that position, the current window area is classified into different classes plus the background layer. Okay, so if you have two classes to classify on, you can plus with the background to classify the window into three classes, right? And for the classification, you can use a CNET, for example. So that was the idea about using the sliding window approach, right? Okay. So of course, that sliding window approach have a lot of drawbacks. First, it's very slow because you have to scan all the location, and it could be very large, right? And in order to improve that sliding window approach, we can have the regional proposal approach. And in this approach, instead of scanning all location, you can align only select. You can align the image to select some potential area, some boxes with a high probability of containing the object, right? And then from that proposal high potential area, you can process equation to classify and to correct the box, the coordinate. Okay, so that's why we are calling this regional proposal approach is two-state detector, right? Two-state object detector. Okay, the first step is to propose the potential region that may contain the object. And then in the second step, we will do the classification of the proposed region and classify them if they are actually an object or not. And you can also try to correct the box, the bounding box of that region. Okay. Okay, so in order to propose a potential region to look at, we can use a selective approach. In the selective search approach, this is something proposed in the ICCV conference in 2011. And in this approach, it can allow you to have fast to do object proposal with in a fast way with a very high recall by over segmenting the image based on intensity of the pixel. So the algorithm, the simplified version of the algorithm is like this. You start by over segmenting the image based on the intensity of the pixel. So this is the starting of the algorithm. You over segmenting the image by that the intensity of the image, right? So you see a lot of different region with different color, right? And then you add the bounding box corresponding to the segmented part, right? To the list of regional proposal, right? So you from this you have a lot of bounding box, corresponding bounding box, and then you can do the grouping of adjacent segment based on similarity, and then you do grouping, and then when you do the grouping, and then you can go back to the step number 1. You add bounding box after the grouping, and then you group it again, and then at the end you can have the smaller number of proposal region to look at to classify the object, right? Okay, so by using the selective search with the neural network, you can have a RCNN network. So RCNN means region-based convex net. You first have to suggest some potential region using other raw algorithms such as selective search, and then use CNN to extract the feature of a region and then classify them by SVM. So that's the idea of RCNN, right? Very simple idea. Okay, from that initial image, we use selective search or other regional proposal algorithm to have the proposed region, and then we use CNN, okay, to extract the feature of a region, and then we use SVM to classify the object if the proposed region is a specific object or not, and we also use a Bebel regression to actually recalibrate the bounding of the object, right? Okay, so that was the idea of RCNN. Input image, you extract around 2000 potential region, and then for it you compute the CNN feature, and then you classify the region to be different classes. Okay. Okay, so that was the RCNN. And And now we discussed about fast RCNN. So in fast RCNN, we push all region about 2000 over the CNN extractor network at the same time. Right, so in RCNN, we extract the region first and then we put 2000 region to the CNN. We extract the feature. And now we put everything over the CNN extractor at once, right? And then we crop the information in the output layer of the CNN instead of cropping the area of the original cropping the area on the original image like the RCNN. So this is the difference in the RCNN. You crop the image first to get a potential region, and then you do CNN feature extraction. In the fast RCNN, you put the entire image into the CNN, right? And then at the last CNN feature map, you do the regional, you do the regional proposal, right? And then I mean the crop feature version pushed through the classification branch and the bbox regetter to actually classify the object and then to calibrate the bounding box of the object. So that's the idea about fast RCNN. Any question about RCNN and fast RCNN? Okay, so in the faster RCNN approach, okay, the difference is in the fast and RCNN, you still have to use an external algorithm to extract the potential region, right? In the faster RCNN, you use a dedicated network to recommend the region instead of selective search. It's also called two-state object detector method. You have the input image, you put the image into the convolution layer, you get the feature map, and from that feature map, you can have a specific regional proposal network to actually propose the potential region to look at. And then also from the feature map, you can merge with the proposed region, and then you can do the classifier on top of it, right? So then you have the network that considers two parts. I mean, extracting the feature and doing the proposal. Right? Okay. Any questions so far about this part? Any question? Okay, if not, then we can have break of 5 minutes and then we will continue. Okay, so let's continue. Okay, so now we discuss the second approach of doing object recognition, object detection. It is one-state object detector, and in this type of network, we also call them non-regional proposal network. So in one state object detector, the network often suggests a dense box grid on the original image, often with a consistent stripe. An XZ box will be classified and corrected for coordinate if the box contains the object or not. I mean, if the box contains the object, then we will correct the coordinate. If not, then we don't have to correct the coordinate. And the classify and corrected for coordinate will be using the CNN network. A one-state network are generally faster and simpler than two-state network, but the accuracy might not be as high. It's faster because you don't need to propose you don't need to propose the potential region, because we already I mean we already split the input into a grid of dense blocks, right? And then we do the classifier on the box, right? So that's what the idea. So that's why one-state network are very faster, because we don't have to do complicated steps to propose the potential region. We just split the input image into grid, and then we do the prediction for that grid. Okay. So here's the idea of YOLO, a very powerful and popular one-state object detector, and you can use this for the application as well. So the idea of YOLO, you only look once, is first to divide the input image into S by S grid, right? And in this case, you see the input image is divided into 1, 2, 3, 7 by 7 grid, right? And then you will do the classification on that, box, each box in the grid, right? For Xbox, you have for each cell in the grid, you have B bounding boxes, right? And what is a bounding boxes? For example, here, when you consider this cell in the grid, right? Every cell have two boxes, and the boxes we have here is this one and that one, and the two boxes are predefined, right? Okay, so in that case, you don't need to do complicated work for regional proposal. You just use the predefined boxes, right? Okay. Okay, so besides the bounding box, for each cell, you have the confidence score. The confidence score is equal to, it compute by this following formula. Is equal to the probability of having the object in that cell, right, multiplied with the IOU score, insertion over union score. The overlap, the intersection between the routers and the predicted bounding box, right? Okay, so that's the so that in this case, you see for every cell. Okay, so how to say it clearer for you? Okay, so take a look into this slide. So we have the input image. We split them into 7x7 grid, and it is our grid 7x7. And then in the grid we have different cell, right? And for the cell, for each cell we have 2 bounding box, right? And in order to to keep the information about the bounding box, or to predict the bounding box, we need to predict the x, y, the width, and the height. That means the coordinate of the top left point, and then the width and the height, right? And then the confidence score. The confidence score is the probability of that cell containing the object multiplied with the IOU score. Okay, so this is the information about the first bounding box, right? And then we have here, this is the information about the second bounding box, right? Because in YOLO version 1, Excel have the 2 bounding box. Okay. So, and then we need to predict what? We need to predict the, the class for that cell. If that cell containing the object and which object is belong to. For example, in the data set we have 20 classes. Then each cell here will need to be associated with the class information, and we need to adding 20 more element into that cell. It concept Excel element is corresponding to the probability of the cell to be a specific class, such as here the probability if the cell belong to a cat, if the cell belong to a bird, and if the cell belong to the object. So basically for the YOLO network, from the input image, right, you will transform the input image into this activation map, or a new image in a new dimension, and it's a 7x7, and then this dimension 5, 5, and 30. I think it's 30. Okay. Okay, so here's the network architecture of YOLO version 1. You have the input image, and then you have different convolution layer, and then at the end you have the activation map 7x7 and 1024 channel, and then you use the fully connected layer that to flatten the presentation, and then you reshape that to be a 7x7 30, the actual output you want from the image, right? So in that 7x7 30, you have a different cell, and for each different cell you have 30 elements corresponding to the B-box projection of the B-box number 1, B-box number 2, and then the class probability. Okay. Is there any question about the YOLO architecture? Hello.
Em thầy là mình chọn bounding box hợp lý ở đây là mình chọn như thế nào ạ?
For the bounding box here, for the bounding box here, what can I say for you? So actually, I mean, for the grid, you so initially when you have the training data sets, right? You have the image and then the routers, right? And you can do some kind of small statistic on the routers to see what are the most common shape for the object, and then you can do clustering the shape into 2 cluster. For YOLO version 1, you have 2 bounding box, and then from that small statistic you can choose the predefined bounding box for the YOLO network. Is that okay? Is that okay?
Thầy có thể giải thích lại không? Em vẫn chưa hiểu.
Tức là nhá, với cái mạng YOLO này đúng không? Thì ok là cái mà mình sẽ cần phải set khi mà mình chạy ấy, đúng không? Là mình chia cái mạng input image của chúng ta thành cái lưới kích thước bao nhiêu và bao nhiêu cái bounding box, đúng không? Và ở mỗi một cái bounding box ok, với cái YOLO version 1 này thì chúng ta sẽ predict cái bounding box chứ chúng ta không predict cái độ, tức là cái độ xê dịch đâu nhỉ? Chúng ta predict cái bounding box em ạ. Thế nên là chúng ta sẽ không chọn cái bounding box với cái YOLO version 1. Chúng ta sẽ chỉ chọn là với mỗi cái cell chúng ta có bao nhiêu cái bounding box rồi. Với YOLO version 2 ấy, trở lên ấy, thì lúc đấy thì chúng ta mới là có cái define cái bounding box và sau đó chúng ta sẽ guess cái gap giữa cái bounding box routers với cái nó predict. Tức là predict cái offset ấy, với cái anchor box, tức là cái mà chúng ta là đề xuất ấy, khi khởi tạo. Ok, thì tóm lại để cho đỡ nhầm lẫn thì chúng ta không nói về cái YOLO version 2 nhé, chúng ta chỉ nói về YOLO version 1. Version 1 thì ok là gì? Chúng ta sẽ là gì? Chỉ define là ok là mỗi một cái cell thì sẽ có bao nhiêu cái bounding box và sau đó chúng ta sẽ đi predict cái bounding box đấy. Mỗi cái bounding box thì sẽ có cái tọa độ XY này, độ rộng, chiều rộng, chiều cao này và cái confidence score. Ok không em?
Vâng ạ.
Okay. Any other question? Okay, so for the loss, I mean, of the network, right? If you want to train the network, you need to define the loss function. And for the YOLO, the loss consists of different component. In the first component you are seeing here is actually the loss for the bounding box location, the routers, and then the predicted location y, right? And of course you have this term to say that okay, you only consider this loss when there is an object. If not, then you can forget about this, right? And then you have the second component is the loss for the bounding box size. Okay, the first is the location x, y, and then this is the loss for the bounding box size. And again, you have this term to say you only consider this component if there is an object. If not, you don't consider this loss. I mean, and again, this is a constant when there is object. Okay, and this is constant when there is no object. Okay, and this is a loss for the class probability when there is an object, right? You need to predict the object to be one among 20 classes, right? So that is a loss of the YOLO network. Okay. Any question for this? So the S here is the grid size and the B is the number of bounding box, right? And this is hyperparameter. Any question? Okay, so for YOLO, it can make duplicate detection for the same object. And for example, here it can detect it the by, so here it can detect it the by, right? So YOLO can apply non-maximal suppression, I mean, to remove the duplication with lower confidence. And the algorithm might be as simple as this one. You sort the prediction by the confidence score. Okay, for every bounding box you have the confidence score, right? And start from the top score. You ignore any current prediction. If we find any previous prediction that have the same class and the IOU intersection over union bigger than half with the current prediction, right? And then you repeat step 2 until all prediction are checked, right? And that non-maximal suppression algorithm to gather the box to give the final result. And finally, you see, you have this is the final prediction for the dog, and this is final prediction for the bicycle. You see, maybe for the dog you have other, but you keep the one with the highest confidence score and remove the one that overlap with the previous prediction. Any question? Okay, so if not, then we can move on to YOLO version 2. Okay, so this version 2 might relate to the question I got from you guys. Initially, the YOLO make an arbitrary guess on the bounding box. And in the real-life domain, the bounding box are not arbitrary. For example, if it's a car, then the shape would be the rectangle like this one, right? If it's human, then the shape could be, this one with the height much bigger than the width, right? So in YOLO version 5, they create 5 actual boxes with the intended shape, right? And then they predict the offset to act of the actual box above. So we see that the difference from YOLO version 2 and YOLO version 1. In YOLO version 1, you need to predict the box, the bounding box. In YOLO version 2, you have the anchor box, and then you predict the offset of the prediction to the anchor box. And if we constrain the offset value, we can maintain the diversity of the prediction and have each prediction focus on a specific shape. For example, if you see that in the data set, you have the car in the prediction class, then you might focus on the prediction have the following shape by define one of the anchor box to have the shape like the rectangle. Okay. Okay, so for YOLO version 2, instead of having that 2 B box, Excel have a 5 anchor box. And for a network, the anchor will give the following information: the box offset for real number in the range 0, 1, confident that the box is likely to contain the object, objectness score, and probability the distribution of the object in that box for different classes. I mean, they are the same as the YOLO version 1. Only different is break the offset, not the bounding box, right? So in total, Excel have an output number of 5 multiplied with 4 plus 1 plus 20. The number of classes, this is a confidence score, this is the offset, and this is the number of bounding box. So Excel will need to predict 125 in number. Okay, this is the default file anchor box of YOLO version 2. If the cell is here, and then you see different anchor box, right? So in terms of network architecture in YOLO version 2, you have the full connected layer to flatten the activation map, right? And in YOLO version 2, you don't have that connected layer. You just, I mean, reset the activation map by another convolution layer with 125 channel, and then you end up with the final output have the following shape. I mean 7 by 7, 125, and this is I mean 8 element in the grid belong to a cell, and then Excel have a 125 element, right, corresponding to 5 bounding box, and then the probability of different classes. If you use YOLO version 2, you can determine the default size of the anchor box by applying the k-mean on the box set of label the object in the training set, and then you decide the number of I mean, here's the classification in different number of cluster, and this is the average IOU, and then you see you can, for the VOC data set, they choose this cluster to be fine, to be the, I mean, appropriate number of anchor box. Okay, any question for YOLO version 1 and version 2? Okay, if you have no question, then we can break for 5 minutes, and then we will continue. What is the meaning of offset in YOLO version 2? I already told you that in YOLO version 2, you have the anchor boxes, right? And the offset is that to, I mean, to offset mean the way you modify the anchor box to be the final bounding box for the object.
Em thưa thầy ạ. Em muốn hỏi bọn em ở nhóm 8 project ạ, thì sau cái buổi tuần trước thì bọn em có nghe review của thầy và có chỉnh sửa lại project cũng khá nhiều ạ. Thì bọn em cũng đã gửi mail cho thầy, thì khi nào thầy rảnh thầy có thể đọc qua và phản hồi lại bọn em được không ạ?
Nhóm số 8 à?
Vâng ạ.
Email của bọn em là gì?
Dạ.
Email của em là gì nhỉ?
Bạn khác rồi ạ, để thầy đợi em một chút ạ.
Ok, mình thấy đây, bạn
Phạm Đinh Gia Dũng ạ.
Phạm Đinh Gia Dũng.
Vâng, em cảm ơn thầy.
Let's continue. Okay, so we got a question from Khánh saying, why are CNN use SVM to classify the presence of the objects? It was the classification algorithm presented in the paper of CNN. Of course, I mean, you can use other classification as well, such as another, I mean, feed-forward network or whatever, but they use SVM, so that's why we have SVM in CNN. You can experiment with different classification algorithm. It's totally up to you. But the SVM is quite a good classification algorithm. Okay, so now we discuss YOLO version 3. Even for today, you have YOLO version 4 and 5. But now let's discuss YOLO version 3. In YOLO version 3, they introduce some, novel mechanism in recent CNN network, such as a residual skip connection and upsampling mechanism. So, for example, in YOLO v3, where the residual skip connection, yes. So, for example, this architecture is much more clearer. You have the input image, and then you have the image that go through a new breakbone. It's DACnet 53 breakbone CNN network with special configuration, and in that network you have a lot of convolution and skip connection, and then instead of doing the prediction of the final activation map, you are actually doing upsampling. For example, this is the output of the DACnet 53, and the output will be put through the YOLO detection block, and then the output convolution layer, and then you have the activation map with the size of 1919, right? So from that output, you also do upsampling, and then you can concatenate with the activation map in the earlier layer with the size of 38 TTS, right? And now you have a second scale of the image, and now it is the third scale. You are also upsampling, and then you concatenate with the activation map in the earlier layer with the size of 76, and then you got another output at this scale, and then you do the prediction in the 3 scale, right? So if you compare the YOLO version 3 and YOLO version 2 and 1, you can see that the number of blocks is much more bigger, because they do the you do the classification with 3 different scale, and then in the grid you see it's a 2 it's fine again grid, right? So that in YOLO version 3 it is not actually faster than YOLO version 1 and 2, but it's more accurate in terms of object recognition, right? The drawback of YOLO version 1 and 2 is it is hard to recognize object with small size. So that's why in YOLO version 3 they do upscaling, sampling the image, and then predict it with a higher resolution. Okay. So again, I must say it's not faster, but it's more accurate than the YOLO version 1 and 2. Okay, another type of single source detector is SSD. It's similar to YOLO, but the box grid is denser, and there are many grids with different box size. And also for SSD, they use another breakpoint network architecture than the one we see in the YOLO. And they also do data augmentation and hard negative mining. Hard negative mining is a mechanism to actually keep the number of samples for the positive class and negative class to be equivalent, and then it will improve the classification score. And data augmentation is something that we already discussed lately in the training neural network. You can actually flip and image and do whatever, and then you have more data. Okay, for the SSD, the user background is VGG 16, so it's different from the YOLO. And then they have an additional convolution layer behind the layer of the Blackboard network. And they also, as the YOLO version 3, they detect the object at different level in the network and multiple scale. So you see here they have around 8,732 bounding box, which is more than that of YOLO, right? They also use non-maximal suppression to remove duplication prediction of the network. Okay. In terms of objective function for the SSD, the observation also consider two parts. One is for the bounding box, and one for the classification score, right? Okay, so in this final slide, you see the evolution of different neural network for object detection problem. You have RCNN, which was presented like 10 years ago, and then in 2015 you have fast RCNN, and then you have faster RCNN, and then you have YOLO in 2016, and then now that you can have the M2DAT. This is something presented in the AI conference in 2019. Of course, I mean, if you take a look into the recent research, you might see YOLO version 4 and 5 and also network as well, right? So it's really hard for to keep up to date to the evolution of the domain nowadays, because it's too much research into this direction. So if you compare one state versus two-state network, the two-state much more, and not much more, but a bit more accurate. But the one state has the advantages of being faster and simpler, right? And it is a representation of the two state, and it is a representation of the one state. Okay, so for YOLO version 2, you see it really fast, right? And you can run the YOLO model in in the device, such as in the Raspberry Pi, whatever, right? It's very, really fast. If you need something more accurate, then you can go with that faster RCNN, whatever. But the trade-off is the CPU running time. It's much costly in terms of execution time, right? Okay. another comparison. This is YOLO and then the Retina Net. You know, if you chase accuracy with the performance, the speed, then YOLO is much more faster, but the accuracy is less in comparison to Retina Net, right? Okay. Okay, so that's all for today. So với cái bài của nhóm số 8 ấy thì mình nghĩ là cơ bản thì nếu mà bọn em như vậy thì mình nghĩ cũng có vẻ ok rồi, chắc là cũng không cứ làm theo cái plan đấy thôi nhá. Ok, có ai câu hỏi gì trong bài học này không nhỉ? Có ai câu hỏi gì không?
Em thầy ạ, video detection thì cũng dùng mấy model này ạ?
Video detection em nói cụ thể là như thế nào?
Ví dụ như trong cái project có cái project về video detection ạ.
Nó có nhiều mô hình chứ. Nếu em xem video làm chuỗi của các hình ảnh gọi là độc lập ấy thì em hoàn toàn có thể là xử lý từng cái frame ảnh một, đúng không? Thế nhưng thực tế thì các cái hình ảnh trong video nó không phải độc lập mà nó có cái mối liên hệ về ngữ nghĩa với nhau. Ví dụ như là tại vì các cái đối tượng trong ngoài thực tế này nó không thể di chuyển quá nhanh được, đúng không? Giữa các frame và các frame thường nó sẽ có độ overlap tương đối là lớn. Thế nên là cũng có rất nhiều cái giải thuật mà khi xử lý video ấy, thì người ta có thể sử dụng cái thông tin có được từ các frame trước để mà có thể là detect các cái đối tượng ở cái frame sau đó. Thì cái này thì mọi người phải tức là tùy theo là cái hướng tiếp cận mà bọn em định sử dụng sẽ là cái gì. Nhưng mà hầu hết các giải pháp mà xử lý video tốt thì nó đều phải kết hợp là thông tin của các cái frame liên quan với nhau, chứ nó không xử lý từng cái frame cách độc lập đâu.
Cảm ơn thầy ạ.
Rồi có ai có câu hỏi gì không nhỉ? Ok, thế thì mọi người tiếp tục với cái bài tập lớn của mọi người nhé. Ok thì chắc là chúng ta cũng không còn nhiều thời gian nữa. Mọi người cố gắng là làm sao có một cái bài tập lớn cho nó tốt để đánh giá cái điểm giữa kỳ của mọi người. Rồi, thế chào mọi người nhá. Bye bye nhá.
Em thầy.